Virtual's demo 2 addresses active safety on a driverless shuttle with the collaboration of Tecnalia, DHI, Third, and CEA. It deploys a fault-tolerant localization system that allows the shuttle to continue on service even with a failure in some of the sensors. It includes the definition and execution of an evasive maneuver in critical situations, taking into account the safety of the occupants of the shuttle. Furthermore, a visual and audited HMI is tailored to keep the occupants informed of the status at all times and to provide instructions when needed.
In Demonstrator 2, we are deploying two specific use cases. In the first one, we want to test the capability of the shuttle to arrive safely to the bus stop, and with enough precision so that passengers can get in and get out safely. For that, it is critical to come with the support from infrastructure that will improve the localization system of the shuttle. In the second use case, we want to test the capability of the shuttle to execute critical maneuvers. Maneuvers that not only consider the external risk, but that also consider the comfort and the risk for the passengers inside the shuttle.
At our Virtual, we have developed an infrastructure-based positioning system that leverages 3D object recognition to accurately locate the shuttle. Our system is built using a combination of sensors, including a dual antenna GNSS, which serve for two purposes: providing a place-time reference and determining the infrastructure global position for transformation. We also use a surveillance camera and a solid-state LiDAR to detect the shuttle. To achieve accurate localization, we collect data from our shuttle and train a model capable of pinpointing the vehicle position within 20 centimeters. This positional data is then transmitted to the vehicle via V2X communication enabled by the roadside URI.
For communication system, we have implemented collective perception message to transmit information about detected objects from the infrastructure to the vehicle following the ITS G5 standard. The system uses consigned devices, an onboard unit installed in the vehicle, and a roadside unit connected to the infrastructure. This setup allows the vehicle to receive key data such as object position, size, and detection time over a wide range, giving it enough time to plan and react accordingly.
In our tool, we have developed a fault-tolerant localization system, which is in charge of providing a reliable localization log. This output can then be used by the decision and control modules to guide the vehicle precise. It is based on the fusion of the different in-vehicle localization sources. This is GNSS and LiDAR-based localization with the infrastructure-based localization. This multi-source configuration enables a road's localization even in the events of degradation or disconnection of one or more sources.
The shuttle's decision and control system is based on the Autobus Foundation stack, which already incorporates the execution of basic maneuvers such as lane change or lane keeping, which is the one used for the use case 1. In the case of the use case 2, this model was upgraded to support the execution of more critical maneuvers using trajectory specifically designed for the shuttle's dynamic considering passengers. In the case of the control model, it used a model predictive control to govern the lateral actions based on a kinematic bicycle model, and for the longitudinal aspect, it used a proportional interactive derivative controller.
Hello, my name is Christian Boltzmacher and I'm a research engineer at EA Limited. CEA is working together with Tecnalia on the autonomous shuttle, and we are providing an internal HMI. This HMI focuses on safety-related messages. When, for example, the shuttle is breaking down on the road, appropriate messages will be shown on our interface. This interface is based on a state machine, but there's also a rule-based approach depending on what is detected inside the shuttle. So the content of the HMI can adapt to things which are happening inside or even outside the shuttle.
At Center for Research and Technology at DAS, we perform multi-body dynamic simulation with active human model with muscle control in order to study the human response under different physical accelerations.